Okay, physics class, it's time for assignment number 5. This is the trickiest one, ostensibly, so let's give it a shot. Assignment number 5 takes us to, whoa, this one. So I'm going to take my time on this one because I want to make sure that I'm not just solving it, but showing you how others like it can be solved. So we have a total of 8 resistors. Lots of resistors. And let's sketch this out, okay? Do I have 8 colors? 1, 2, 3, 4, 5, 6. Yeah, I've got 8 colors. So I'll go ahead and try and color code these. Actually, you know what? No, I'm going to color code them after I combine them. Okay, so there's R1, R2, R3, R4, R5, R6, and finally R7 and R8. Okay, so they have various values, but I don't want to clutter up my drawing, and you can see them on the screen and in the assignment. Right. So we want to try and think of how electricity flows through this circuit. So there are a couple of things which are kind of obvious and a couple of things that are not. Let's do the obvious ones first. So I see 7 and 8 sharing this last little leg of the circuit. I say last because it's furthest to the right, but if you went through them, that's halfway through. So let's take 7 and 8 and smush them together, and just compress them into a single resistor. Now, according to this diagram, they're each 50. And since they are in series, then they add up directly. 50 plus 50 is 100. So I can replace this with a single 100 ohm resistor. I'm going to go ahead and do that now. So here comes the sketch. Just give me a sec. 1, 2, 3, 4, 5, 6. Here we go. 7 and 8. And this is a single resistor whose resistance is 100. Let me go ahead and throw some labels on these. This is 1, 2, 3, 4, 5, and 6. Okay. Now what? Well, there are so many resistors here, it's hard to know where to start. However, if we were to look at just small parts of it in isolation, then it gets a little less overwhelming and we can try to make some sense of it. So let me cover up part of it. Just look at that. If you're going to go out this side of the circuit, all the way out at the end, the only way to get here is through there. Okay, which means that we're kind of looking at the circuit equivalent of like the one in number 2. Did it look like that? It was like resistor 1, 2, 3, and 4, something like that. Which means that these two are in parallel with each other, and then we could have this, that, and this in series. So what I'm going to do is I'm going to take this and replace it with an equivalent. Now, according to the diagram, resistor 6 has a resistance of 50, and this is 100. So I need to find the equivalent resistance of a 50 and a 100 in parallel. 1 divided by 1 divided by 50 plus 1 divided by 100. It is 33.3 repeating. Okay, well, let's get to sketching. One, two, three, 4, this one has a resistance of 33.3, and here's 5. Okay, so we're making some progress here. Let's see what's next, though. So again, at the end, I've got 3 in a row in series, 4, and then this 33.3 followed by resistor 5. If you just go through resistor 1, none of that matters. If you go through resistor 2, none of that matters. If you go through resistor 3, none of that matters. However, if you take this path, you've got to go through all 3 of these, which means these 3 are in series and they add up in series. Let's see what resistor 4 is. Resistor 4 has a resistance of 10, and resistor 5 has a resistance of 50. So we've got 10 plus 33.3 plus 50. 10 plus 33.3 plus 50. 93.3 93.3. Okay, we are almost to the point where we can finish this. Just let me get another piece of paper. Okay. So I can redraw this with that 93.3 in place. It's going to look like this. Resistor 1, resistor 2, resistor 3, and then this thing. Let me get the color. .3. Okay, that's that, but with this replaced with that single one. All right. So, what about these 4 resistors? The geometry of this is actually a little misleading. If I were to cancel those wires but keep the connections, it would look kind of like this. Got 1, 2, and then there's no space between the path for 3 and this and the path for this one, so they just start together. Here's 3, and here is our green one. See, these are equivalent. That wire didn't need to be there. But, you know, those don't need to be there. Those don't need to be there. Which means that this whole thing is equivalent to this lovely thing. Oops, sorry. Yeah, because that really offended you. All right, here we go. Resistor 1, resistor 2, resistor 3 and resistor green, they're all in parallel with each other. If you like, you could also draw it like this. One, two, three. Kind of make it look like a little globe. 4. Those are all the same picture. The geometry doesn't matter. What matters is the connectedness of it. When I say geometry, I mean it doesn't need to be rectangles. It doesn't need to be this far away. The wires are completely flexible. So in order to solve this, all you need to do is add them all up together in parallel. And that's the 1 over 1, right? So let's go ahead and do that. Clear that. 1 over. Okay, 1 over the value of resistor 1 is 10. Oh, it's 10, 10, 10. They're all 10, except for the last one. So, oh, wrong one. So 1 over 10 plus, that's resistor 1. Resistor 2 is also 1 over 10 plus. Resistor 3 is also 1 over 10 plus 1 over 93.3. Okay, 3.22. The final resistance of this is 3.22 ohms. Very, very small resistance. Okay, how can you have only 3.22 ohms with all of these in here, all these 50s, all these 10s? Well, it's because you've got 10 ohms of resistance, but the electricity can split up between all of these so that, using my analogy of traffic flow, yeah, there's all these roads with delays, but with so many options, the traffic is never backed up. So you end up with a resistance of 3.22. Okay, I hope that didn't give you too much of a headache. I hope that this is helpful, even maybe a little enjoyable. I can hope. Anyway, hey, I'll see you next week with new stuff. We're going to bring back Ohm's Law. Hooray. And do more than just equivalent resistance. You just need to be able to do equivalent resistance to do all the other interesting stuff. All right. Bye-bye.